Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that in the previous class we had talked about what is bond and we looked at what is the price of the bond, interest rates and so on, and we had defined what is going to be the duration of the bond, and we had identified that the duration of the bond is synonymous with the risk that is associated with the bond, and the risk associated with the bond here means in the context of how the price of the bond changes depending on how the interest rate actually moves during the lifetime of the bond, and this usually is a risk that will arise when the owner of the bond decides to liquidate the bond prior to the maturity of the bond. So, in today's class we will extend this notion and we will talk a little bit about what is certain properties of the duration of a bond and a portfolio of bonds, and we will talk about the concept of risk mitigation of a portfolio of bonds by using the notion of immunization. So, accordingly we start this lecture with the definition of something called yield to maturity. So, the yield to maturity is an interest rate which are denoted by R star such that it is given by the expression that the bond price at time 0 is given by C of t into 1 plus R star raised to minus t is equal to 1 to capital T. So, this is some sort of a uniform interest rate that is applicable, so that the present value of the coupon becomes equal to the price of the bond. Then for the particular case of all the coupons being identical to C for t is equal to 1, 2 all the way to capital T, the yield to maturity is an interest rate R star such that B of 0 is equal to summation C into 1 plus R star raised to minus t is equal to 1 to capital T plus B of capital T into 1 plus R star raised to minus capital T. We next talk about some properties of duration. So, we now discuss a few properties of duration, particularly the duration as a function of three things, namely coupon rate, the yield to maturity and the maturity itself. So, start off with the first property, which says that the duration d in terms of the coupon rate for the particular case of C of t is equal to C for t is equal to 1, 2 all the way to capital T is given by d is equal to 1 plus 1 over r plus capital T into r minus little c over b of capital T minus 1 plus r divided by c over b of capital T into 1 plus r raised to t minus 1 plus r. So, the proof for this goes as follows. We first begin by recalling that the definition of duration is minus of proportional change in the bond price divided by d of 1 plus r over 1 plus r, and your b. So, we are just recalling the definition of d and b. So, this was c over r into 1 minus 1 over r 1 over 1 plus r raised to t plus b of capital T divided by 1 plus r raised to capital T. So, this was the bond price when we had all the coupons to be identically little c. Therefore, b over b of capital T, this is going to be equal to 1 over r within bracket c over b of capital T into 1 minus 1 over 1 plus r raised to capital T plus c over 1 plus r raised to capital T. This implies that log of b over b of capital T, this is going to be equal to minus log of r plus log of c over b of capital T into 1 minus 1 over 1 plus r raised to capital T plus r over 1 plus r raised to capital T. So, just a slight correction here, this should be actually little r. So, now we differentiate with respect to r. So, this will give me d of r of log of b over b of capital T. This is nothing but d log of b over dr, and this is 1 over b db dr, and this becomes minus 1 over r plus c over b of t, t into 1 plus r raised to minus t minus 1 plus 1 plus r raised to minus t plus r into 1 plus r raised to minus t minus 1 within bracket minus capital T divided by c over b of capital T into 1 minus 1 plus r raised to minus capital T plus r into 1 plus r raised to minus capital T. So, multiplying this expression by minus of 1 plus r, so that we obtain the duration d, we obtain the expression d is equal to 1 plus 1 over r plus capital T into r minus c over b of capital T minus of 1 plus r divided by c over b of capital T into 1 plus r raised to t minus 1 plus r. We next come to the property the second property, that is the duration in terms of yield to maturity. So, the duration in terms of yield to maturity is given by dd of dr is equal to minus 1 plus r raised to minus 1 into Vd, where this new notation Vd is the dispersion or a variance of payment times of the bond and consequently this is positive. So, the proof for this goes as follows. So, recall that d is equal to 1 over b of r. So, it is just 1 over the bond price, t is equal to 1 to capital T, T c of little t into 1 plus r raised to minus t. So, this is the definition, and I have specified b of r to indicate that this is dependent on r. So, therefore, dd of dr, this becomes what? This becomes minus 1 over b square of r within bracket summation t is equal to 1 to capital T, t square c of t into 1 plus r raised to minus t minus 1 into b of r plus summation t is equal to 1 to capital T, t of c t into 1 plus r raised to minus t into b prime of r. And this becomes equal to minus of 1 plus r raised to minus 1 within bracket summation t is equal to 1 to capital T, t square c of t 1 plus r raised to minus t divided by b of r plus 1 plus r b prime of r over b of r into summation t c of t 1 plus r raised to minus 1 over b of r. And this becomes minus of 1 plus r raised to minus 1 within bracket summation t square c of t into 1 plus r raised to minus t minus 1 over t is equal to 1 to capital T over b of r plus this is by definition minus of d and this by definition is just d. So, we get minus of 1 plus r raised to minus 1 within bracket summation t is equal to 1 to capital T, t square c of t into 1 plus r raised to minus t minus 1 over b of r minus d square. So, let us define w d of t to be c of t into 1 plus r raised to minus t over b of r. Now, if you observe carefully, so observe that summation w d of t, t is equal to 1 to capital T, this is going to be summation c of t into 1 plus r raised to minus t over b of r, t is equal to 1 to capital T, and this summation of the numerator, this is nothing but b of r and this is equal to 1. So, the W d of t defined in this way, this will effectively act as if they are weights. Also, we observe that d is nothing but summation T C t into 1 plus r raised to minus t over b of r, t is equal to 1 to capital T, and this by definition is going to be. So, by definition of W t, remember that this term is going to be W d of t. So, this is t of W d of t, t is equal to 1 to capital T. So, therefore, d d of d r, what is this going to be? This is going to be minus of 1 plus r raised to minus 1 within bracket t square W d of t minus d square, all right. And this is going to be, this can be rewritten as 1 plus r raised to minus 1. So, the summation is 1 from t equal to 1 to capital T. So, this is going to be summation t is equal to 1 to capital T into t square W d of t minus twice d square plus d square, and this can be written as minus of 1 plus r raised to minus 1 of summation t is equal to 1 to capital T, t square W d of t minus twice d, and one of the d's can now be replaced with this expression. So, this will become summation t is equal to 1 to capital T, t W d of t plus d square, and I will have, instead of 1, I will now make use of this expression summation W d of t, t is equal to 1 to capital T. And this is going to be nothing but minus of 1 plus r raised to minus 1 summation t is equal to 1 to capital T W d of t, t square minus twice T d plus d square, and this can be written as minus of 1 plus r raised to minus 1 summation t is equal to 1 to capital T W d of t into t minus d whole square, and this can be written as 1 plus r raised to minus 1 into V d. So, here V d is nothing but summation W d of t, t is equal to 1 to capital T into t minus d square. And remember, what was my V d? V d was defined as the dispersion or variance of the payment times of the bond. So, this is going to be the variance of the payment time of the bonds. Here t is like the random variable. So, we come to the last of the three properties, and this property is that the following properties of duration in terms of maturity of bonds hold. So, I will enumerate the properties. So, for a 0 coupon bond, the duration is equal to maturity. The second property is that from the relationship between duration and the coupon bond, we obtain that the duration tends to 1 plus 1 over r in case of a perpetual bond, that is at t tends to infinity, for any fixed coupon C, and thirdly, in case of coupons with coupon rate greater than or smaller than yield to maturity increasing maturity results in increasing followed by maximum and then decreasing duration tending towards 1 plus 1 over r. So, this means that in case of coupons with when the coupon rate is greater than yield to maturity, it results in increasing duration tending towards 1 plus 1 over r, and when the coupon rate is smaller than the yield to maturity, it follows that initially it is an increasing duration followed by maximum and then decreasing duration. All right. So, for greater than the yield to maturity, we will have a increasing duration, and when it is less than the yield to maturity, we will have a piecewise kind of a behavior, where there is an increasing followed by the maximum and then there is a decreasing behavior of the duration, in both case eventually tending to 1 plus 1 over r. Okay, so now we come to a very important topic, and that is on looking at what is going to be the duration of a portfolio of bonds. Remember that our whole concept of bond portfolio optimization is driven by the idea that the bonds are also susceptible to risk, and accordingly we need to make an appropriate choice of the weights of the bonds in a portfolio, driven by what is the risk associated with the portfolio of the bond, and that risk association is reflected through the duration of the portfolio of bonds. So, naturally the next thing that we will need to look at is we are going to look at the duration in case of a portfolio of bonds comprising of say n number of bonds. So, accordingly we start the topic of duration in case of a bond portfolio. So, we consider a bond portfolio comprising of say capital N number of bonds, and we let the number of units. So, I am proceeding in exactly the same way that I had done in case of stock. So, that let the number of units of the kth bond out of this capital N bond in the portfolio be denoted by say N subscript k, with the corresponding prices being Bk of r for k is equal to 1 to all the way to capital N. Then the value of the portfolio is given by the following. So, if the price of the kth bond is Bk of r, and if you buy Nk number of bonds, so that means the amount invested in the kth bond is Nk into Bk of r, and I sum this over the capital N number of bonds, and that is going to give me the value of the portfolio, which I will denote by B of P. Okay. So, now what we do is that we differentiate Bp with respect to r to obtain dBp over dr. What is this going to be? This is going to be summation nk, remember nk is a constant, k is equal to 1 to n, into dbk over dr into of r. Now, what I can do is that I can then multiply both sides by minus of 1 plus r divided by bp of r. So, I get minus of 1 plus r over bp of r into dbp dr, and this is going to be summation nk bk of r over bp of r into minus of 1 plus r over bk of r into dbk over dr. So, here this dbk dr remains as it is, the nk remains as it is. We multiply both sides by minus of 1 plus r divided by bp of r, and we have this term bk of r on the numerator, which can cancel out with the bk of r in the denominator. So, I have just added these two terms, so that I can get the duration on the right hand side. So, this will give me that. So, by definition the left hand side is nothing but the duration of the portfolio, and this is going to be nothing but summation nk bk of r over bp of r, k is equal to 1 to capital N, with the remaining term that you see here, that by definition is dk. So, here what do we have? Here your dp is the duration of the bond portfolio, your dk is the duration of the kth bond. So, further we observe that what is going to be nk bk of r, since this is the amount invested in the kth bond, divided by bp of r, that is the total investment, and this I will define as wk. And see, this is the total investment in the kth bond divided by the total investment in the portfolio. So, this which I identify as wk is obviously going to be by definition the weight of the kth bond in the bond portfolio. And you observe that summation of wk, k is equal to 1 to capital N, this is going to be summation nk bk of r over k is equal to 1 to capital N divided by bp of r. This is going to be simply bp of r over bp of r is equal to 1. So, it satisfies the condition of the definition of the weights. So, let me call this star. So, therefore, star implies that dp is going to be summation of wk dk, k is equal to 1 to capital N. So, this means that the duration of the bond portfolio, just like in case of stocks, is nothing but the weighted sum of the duration of the bonds in the portfolio. Okay, so now that we have defined what is going to be the duration of a bond portfolio, it is now imperative that we move on to how to use this concept of the duration of a bond in order to take care of the risk aspect of the bond, that is for better risk management of my bond portfolio. And this concept of the management of a bond portfolio, as far as the risk of it is concerned, that arises from the movement of the underlying interest rate, is what is known as the process of immunization. So, accordingly we start off with our discussion on immunization. So, in order to motivate this, let me first observe that while bonds have assured returns assuming that there is no default by the issuer of the bond. But if the interest rates goes up, the price of the bond will come down, and consequently the owner of the bond will suffer losses in case the bond owner intends to liquidate the bond. The notion of immunization of a bond means that the horizon will equal the duration of the bond and the basic driving principle is that the duration of the portfolio of bonds must equal the investor's horizon. So, armed with this motivation here, we accordingly can say that immunization is defined as a bond portfolio management approach wherein the investment in a bond portfolio is protected against movement of interest rates, typically parallel movements of interest rate for liquid bonds. And this is done by making the horizon of the investor equal to the duration of the bond portfolio. So, this means that if you are considering the portfolio of bonds, so obviously that means that it is going to be constituted by purchasing several number of bonds. Now, each of those bonds will have a duration. So, you have to decide on the appropriate weight that you have to assign to each of those bonds, so that the weighted sum of the duration of the bonds and the appropriate choice here means the appropriate choice of the corresponding weights, and the consequent weighted sum of the durations is going to be the duration of the portfolio of bonds. And in order to carry out the process of immunization, you will need that the duration of this bond portfolio given by the weighted sum of the duration of the individual bonds must be such that the duration is equal to the horizon of the investor's point of view, and accordingly this becomes like an optimization problem while you decide what is going to be the weights, so that DP becomes equal to the horizon H in case of each of the individual investors. So, in order to be a little more specific, so let us say that B0 be today's, that means at time t equal to 0, price of a bond, and let BH be the value of the bond at horizon H. The rate of return for the time length H, that means from this during the interval 0 to capital of H, is given by the relation B0 into 1 plus RH raised to H is equal to BH, which implies that. So, I have specified what is B0 and I have specified what is H and what is my B of H. So, accordingly I have this relation, and where my RH is the rate of return for the time length H, and this gives me that R of H is equal to BH over B0 raised to 1 over H minus 1. Now, here you observe carefully that this BH, that is the amount of the value of the bond at the horizon H, is a random variable. Now, suppose that the investor has bought a bond today at a spot rate of R0t, which I will denote as R subscript 0, with the prevailing. So, at the time of purchase of the bond, the interest rate was R naught given by this, with the prevailing interest rate, and consequent to that the prevailing interest rate for the next day having moved to some R which is different from R naught. So, the consequence of this is the following, that the resulting or the consequent value of the bond, which are denoted by B of R, this satisfies that B of R is equal to BH, and then now that the price of the bond is B of R, but so this is going to be related to B of H, as B of H is equal to B of R into 1 plus R raised to H. But we recall from this relation here that B of H is equal to B0 into 1 plus RH raised to H. So, now therefore, what do we have? We can equate both the expression for BH and get B0 into 1 plus RH raised to H is equal to B of R into 1 plus R raised to H, which implies that our R of H is equal to BR over B0 into 1 over h into 1 plus r minus 1. Now, note that here B0 is fixed and hence RH is dependent. So, RH is a function of B0, Br and 1 which by extension is R and 1 over H. So, this depends on B0, R and H. Now, amongst this, since B0 is fixed, so consequently RH is dependent on only H and R, and of course, by extension it is going to depend on B of R. We are now, once we have this setup ready for us, so we are now equipped to state and prove the immunization theorems. So, let the duration of the bond be d, and this can be extended to a bond portfolio. Further, let the term structure of interest rates be horizontal, that is a straight line. So, that is all maturities have the same yield. So, we are just starting off with a very simple case. Then the purchaser of the bond is immunized from any changes in the bond price resulting from any parallel change in the interest rate structure, provided that means subject to the condition that the horizon H of the bond owner is equal to the duration of capital D. So, now note that this can be proved in case of any parallel movement in the term structure of interest rates. So, we now state the following theorem in a very the statement of the theorem is very brief, that D is equal to H. So, let us start off with the proof of this theorem. Now, recall that what we had? We had B0 into 1 plus R subscript H raised to H was BH, and this was the same as BR into 1 plus R raised to capital H, and the other relation that we had was R of capital H was BR over B0 raised to 1 over H multiplied by 1 plus R minus 1. So, we recall these two relations. And what is going to be your goal? The goal is to minimize RH, which is equivalent to minimizing BH. Therefore, we have dBH over dr. What is this going to be? This is going to be ddr of Br. So, I replace the expression of BH with the one which had with this expression, that is Br into 1 plus r raised to h, and this can be written as B prime of r into 1 plus r raised to h plus h into Br into 1 plus r raised to h minus 1. Now, since I am trying to minimize BH, so this means that I have to take this equal to 0. Okay. So, what do we want? So, we want that at the initial time point that B prime of r is equal to 0 at r is equal to r naught, right, because we want this to be equal to 0. Then if I substitute r equal to r naught, we get that B prime of r naught into 1 plus r naught raised to h plus h into B naught, h into B of r naught into 1 plus r naught raised to h minus 1. This is going to be equal to 0, and which upon solving we get h. So, we solve for h and we obtain that h is equal to minus of 1 plus r naught divided by B of r naught into B prime of r naught, which is nothing but the duration of the bond at the initial time when the interest rate was r naught. And hence, so therefore, we have our h is equal to d. Okay. So, now we have to prove another theorem, and then this theorem is that the second derivative is positive. Remember that we are trying to minimize BH. So, we have got dB dH equal to 0, and for minimization we have to show that the second derivative is positive. So, now the proof goes as follows, that the relation BH is equal to B of r into 1 plus r raised to h this implies. So, if I take log on both the sides, I get log of BH is equal to log of BR plus h into log of 1 plus r. So, then differentiating with respect to r, we get dBH of dr is equal to 1 over Br into dB dr plus h over 1 plus r. So, the derivative of these two expression. Now, what is this? dB over dB dr over Br, this is nothing but this can be written as minus d over 1 plus r plus h over 1 plus r. And since from the previous theorem d is equal to h, so this becomes equal to 0. So, therefore, d square ln of Bh over dr square, the second derivative, this is 1 over 1 plus r whole square into minus of 1 plus r dd dr plus d minus h. This can be written, now since d is equal to h, so this can be written as minus 1 over 1 plus r dd over dr. Now, this can be rewritten as minus of 1 plus r raised to minus 1 multiplied by, remember dd over dr, we had that expression as minus of 1 plus r raised to minus 1 into V d. And V d, remember, was the dispersion or something like the variance, and this can be written as 1 over 1 plus r whole square, which is positive, V d is positive, and this entire thing is going to be greater than 0. So, this brings us to the end of this lecture. So, just to do a brief recap, we essentially did two things in this lecture. The first is that we looked at the properties of duration and its behavior vis-a-vis the coupon rate, the yield to maturity and the maturity itself. And the second component that we did was that we looked at the notion of immunization, and we proved two theorems involving the first and the second derivative, and identified that the key component of the process of immunization is that the duration of the bond or the portfolio of bonds must be equal to the horizon of the investor, that is the period for which the investor is looking to hold on to their position. So, in the next class, we will look at an extension of this case to get a slightly better results in terms of assessing the risk of a bond, and that is what is known as the convexity of a bond. Thank you for watching.